Hello, good afternoon, welcome. My name is Stuart Marks. I work at Oracle in the JDK group. I work on what we call the core libraries, which includes a whole bunch of things, including things like collections, which you're here to listen to today. Also Lambda, streams, serialization, RMI, and a few other things besides that. You can find me. My Twitter tag is @StuartMarks, and if you're on Stack Overflow, I occasionally will post some answers there. That's my avatar, in case you are familiar with The Muppet Show. So if you have any questions on Twitter after the talk, if you don't see me around the conference or at one of the events on the Groundbreakers Hub, you can tweet with this hashtag. If you have any questions or feedback, I'll be looking for this hashtag, and I will try to answer your questions or refer you to links or articles or whatever's appropriate. I'll have this hashtag on every page too, so in case you forget it, let me know. Quick question? Post this online? Yes, the slides will be posted online on the conference website after my talk. Okay, so the overview today of the talk is collections corner cases. So the collections framework has been around for a very long time. I'm not going to be talking about anything new today. I'm going to be talking about a few APIs or aspects of the collections API that have been in the collections framework for quite a long time. In fact, I haven't done the research into how long it's been in there, maybe earlier than even JDK 5. Some of it probably dates back to JDK 1.2 when the collections framework was introduced. So I'm going to be covering two topic areas in this talk. One is a concept I'm calling view collections. And the second one is sorted collections and some related issues having to do with comparators and a phrase you may have heard before, which is consistent with equals. And I will explain that in great detail later. All right, view collections. Okay. I'm assuming that most of you are familiar with things like ArrayList, HashMap, and so forth. Those collections contain their elements. If you create an ArrayList and put things into an ArrayList, the ArrayList contains those elements and no other collection contains those elements. View collections are different though. They don't own their own elements. They don't contain their own elements. Instead, what they provide is like a viewport into some other collection or elements stored somewhere else. And so here's a little code snippet for you. Let's create an array that has some strings. So you just have a string array. Now create a string list using arrays.asList, and you pass it that array. What does that actually do? So the array, the list that's returned from arrays.asList holds a reference to that array. And in fact, that string array, you also have that in the variable named array. And those are the same thing. The underlying storage is the same. So if you change an element of the array, that is reflected in the list. And if you change an element in the list, saying list.set, that gets pushed down into the array. And so I think this is a simple case, but I think this is something that people don't understand that often. Sometimes I hear people saying, oh, the list returned from arrays.asList is immutable. That is clearly not the case. If you try this yourself, you can clearly see that the list is not immutable at all. What is interesting about it is you cannot add or remove elements because in Java you cannot change the size of the array, but you can certainly set elements into it. And of course, it is mutable. So here's a diagram that shows what's going on, right? So we have the string array at the bottom, and that's where the strings actually are contained. And then up at the top is arrays.asList. That list there, I've kind of drawn it in a dotted line to say that list doesn't have its own elements. And so if you call get on it, it reaches down into the array and pulls it out and hands it to you. And if you call set, that punches kind of through the list down into the array. So the point here is that the list returned from arrays.asList, that doesn't contain its own elements. Those elements are stored elsewhere and in the underlying string array, as it turns out. Okay, so now I'm going to move on to some more interesting view collections. So map has a very nice family of view collections. So here are a few snippets of code. At the top, we create a hash map. Let's assume it's populated with something. And then the next few lines, we create a key set, and that returns a set of the key type. So in this case, we have a map from integer to string. Key set returns a set of integer, because integer is the key. There's also map.values, and that returns a collection of the value type, which is in this case string. So it's a collection of string. Now it's interesting, it's a collection. It's not a list, it's not a set or anything like that. The reason is that if you think about it, map keys must be unique within that map, but you can have duplicate values. And furthermore, for maps like hash map, there's no ordering relationship. So what's the collection that, or what's the aggregation of just the values of the map? Well, it's just a collection because it can have duplicates. There's no ordering implied, and so it's not a list or a set. So pretty much the only type left is collection. And there's another thing, which is you can get the entry set of a map. So an entry is just a key value pair, and so you can get a set of those entries. And so this is what a map entry looks like. It's a pretty simple interface. Actually, there's a bunch of other stuff. I've simplified this quite a bit. But this is a map.entry, and there's a key, K and V are the key and value types. And you can get the key, you can get the value, and you can also set the value. So that's kind of an interesting wrinkle on that. And I will show you some interesting things you can do with that. All right, so let's look at some diagrams here. We have our hash map from integer to string. And so with a map, of course, if you have the key, you can look up the key and get the corresponding value. And so that's what, so the top row is the keys, and then each of those is associated with a value, and that's what the arrows mean there. So that's what a map is. Now, if you get the key set view, so again, it's a view. The key set is not a set of it, that contains its own elements. The set view contains the set of keys, but it actually refers to the keys in the underlying map. And so those pink areas there are where you can see that's where the relationship is. The key set says, well, I'm the set of keys, but really, those keys are actually contained in the underlying map. And then similar with the values. If I ask for the values collection of a map, then this values collection really refers to the values in the underlying map. And finally, this is a little confusing. It's like, well, the map entry set contains the keys and values of the entire map. Well, what's the difference here? Well, the difference is it's in a different shape. So a map has keys, and there's a relationship between keys and values, but this is a set view of exactly the same information. So a set is a linear collection. You can iterate over it. You can't iterate over a map directly. So it's the same information. You have all the same keys and values, but it's just in a different, it has a different shape, and therefore it's a different type. All right, so what I'm going to do is switch over and do some demos here. All right, so this is JShell. So JShell is a Java read eval print loop program that was introduced in Java 9, I think. Just a brief introduction to it here. Basically, you can type Java expressions or even whole Java programs in here. So if I say 1 + 1, it says, the answer is 2. Or you can type statements. Okay, so I can say print. Let's see, you can create variables, or you can say list.of a, b, right? So what does that do? So notice what's going on here. So I said list.of a, comma, b. That created a list. And it says $3. So if you don't use the return value of a function, JShell will assign that to an automatically created variable. So what is $3? So in JShell, commands to JShell begin with a slash. So I'm going to ask what kind of variable $3 is. And so this is /var. This is completely different from the var feature that was introduced in Java 10. It's quite unfortunate that they have the same name. And actually, I'm going to be using both in this demonstration. So you have to keep this straight. So /var is a JShell command. What variable is $3? And so it tells me $3 is a list of string. Okay, and it knows that because list.of returns a list of something, and I gave it string arguments. Okay, so I've preloaded some stuff here, so you don't have to watch me type them tediously. So ccc.jshell is a bunch of declarations I prepared for this presentation. So let's look at what's going on with a map. So I have created a map, and let's look at what that is, right? So we have a hash map from integer to string, and it has a bunch of keys and values in it, 1, A, 2, B, 3, C, and so forth. So So now I'm using the Java programming language var declaration here. So I'll say keyset equals map.keyset. And so that gives me a set. So it's a set of integer that contains 1, 2, 3, 4, and 5. And so if you look at the values of the map, you can see it's plucked off the keys from the map, and all I can see is just the keys. All right, so similarly, I can say var values, what would I call it? Values equals map.values. And that is a collection of string, and that is the values from the map. And I can also say var entry set. Okay, so that gives me the entry set. Now it's interesting, if you look at the actual map, this is the same thing there, 1A, 2B, 3C, and so forth. It's just that the map is a hash map, and the entry set is a set of map.entries of integer and string. So again, same information, different shape. Now, what can you do with a key set? So remember, back when I was talking about the arrays.aslist, I said arrays.aslist doesn't contain its own elements. They're stored somewhere else. They're stored in the underlying thing. Same thing with the key set values and entry set here. So if I look at the key set, sorry about that. All right, so it has those keys. Now let's put something into the map. So map.put 6f. All right, so one of the things is, you've got to get used to this a little bit. The collections API often returns a value that is not necessarily useful. And so in this case, it returns us the previous value that was associated with 6, and there was nothing, so it returns null. So that's all that is. But if we look at the map, it says, oh, okay, so we have six elements there. Now, notice I didn't get the key set again. I already have a reference to the key set that already exists, and there are 6 keys in there, because remember, the key set is a view of the keys in the underlying map. And same with values, right? There's another value in there, and then also entry set. And same with the entry set. So again, these view collections are just showing us slices of what's in the map. Now, what's also interesting is that you can do side effects, right? So if you have key set, I'm going to say key set.remove 3. So I'm going to remove 3 from the key set. And not at all surprisingly, 3 is gone from the key set. But let's look at the underlying map. The entry corresponding to the map key 3 is also gone. So there used to be a 3C mapping there, and that's gone now. And so same thing's going on. You put something in the map, it's visible in the views. If you change the views, those changes are pushed down into the map. All right, and so that applies to key set values and entry sets. They're restricted. You can't add anything to the key sets. You can't add anything to these views. You can remove things though, and that seems like it's not that useful, but it actually comes in handy a few times. So for instance, you can do things like this. You can use collections bulk operations on these view sets. So you can say, suppose I wanted to remove all of the mappings whose keys are even numbers. So I can say keyset.removeIf, and then the key is an integer, so I can say, so I need to supply a predicate here to the removeIf command. So if the key is even, so if key mod 2 equals 0, then remove that from the key set. And it says true, that means the map was modified. So if you look at key set, oh look, the even ones 2, 4, and 6 are all gone, leaving only 1 and 5. Now, what happened to the underlying map? Those mappings were also removed. And then same with values and the entry set. Okay. Now, entry set is a little weird. It's not quite as useful as it was earlier, now that we've added a variety of bulk operations in Java 8. But there are some things you can do with it. So I wanted to show you just one more quick thing here with the entry set, which is that you can iterate it. And usually what people would do is, before we had the collections bulk operations, you had to write for loops to modify all your collections. And so we can get an iterator over the entry set. And so that's actually the name of the implementation class. So let's ask JShell what it is. It is an iterator of map entry. And so since it's an iterator, we can get one entry out of it by saying next. I'm not going to bother calling hasNext because I know it has some. So let's look at the entry. And so that's the entry corresponding to the mapping from 1 to A, and it is an instance of map.entry. So now that we have an entry, you can say, get key and get value. No big deal, not what you expect. But let's say, let's set the value. Let's set the value to something else. Okay, so if we change the entry, now this is a mapping from 1 to XXX. Big deal. But remember, the entries are also a view into the underlying map. So if we look at the map, when we set a value on the entry, that got pushed all the way back into the underlying map. So, and then, if you look at values again, that's also changed. So anyway, so all these views, they don't have their own elements. They're all different ways of looking at, different views of the underlying hash map. Okay. All right, moving on. So here's kind of an extended example, which I'm not going to bother typing in, so I have a few slides here. Some time ago, I remarked that I get a lot of my material for conference talks on Stack Overflow, and this is no exception. And so what happens is somebody asks a question, and it's a reasonable question, and there's an answer, and the answer is somewhat less reasonable. It's like, okay, so now I have to go answer this. But actually, there are often lessons in this, and so I'll talk to you about what happened in this particular question here. All right, so somebody had and sometimes people have trouble with giving the problem statement, so I've condensed this down. The original questioner had 2 maps, and the maps have an overlapping set of values. And so what he wanted to do was get the keys from the second map that corresponded to values that occurred in both maps. So it's like, okay, that's kind of interesting. Well, you could loop over the maps and see how this works. All right, so if you look at these 2 maps here, 1A, 2B, 3C, and 5A, 6D, 7C, you can eyeball it for a little bit and say, okay, A is a value that occurs in both maps, and C is also a value that occurs in both maps. And so the result we want is the keys from map B, and that's 5 and 7. Okay, that's not too bad. Well, what made this more interesting was that his maps had 15,000 entries in them. And so it's like, obviously you want to write a program to do this, but you also need to pay attention to the algorithms you use. So this turned out to be a little bit of an interesting question. Okay, so the questioner actually, I want to be a good sport here. He gave it a good try. He said, all right, if I have my 2 maps, I can stream the key set of the first map and stream the key set of the second map and get them from both and see if one is in the other, and then increment to counter, and then at the end of that I collect all this. I'm not going to. I wouldn't bother spending too much time trying to understand what this does, but this is sort of like 2 nested for loops over the keys of each map, and then once you have those, you say, once I have both keys, is the value corresponding to this key the same as the value corresponding to the other key? If it is, then that's a common one, and then and that's how we find out one of the keys for our result. But if it's like 2 nested for loops and there are thousands and thousands of entries, then that's an n-squared algorithm. And so he recognized this. He says, this is too slow, and there has to be a better way to do this. So he's right. Okay, so let's try to improve this. So one of the other answers on the Stack Overflow question was, oh, okay, so instead of looping over both keys, you can streaming over the entries, you can say, just use the contains method. So now this is interesting. So he says map a.values contains. It's like, oh, okay, great. So he's using one of these nice view collections and invoking the contains operation on it. And so if this value is contained in the other map's value set, then we know there's a common one. So get the corresponding key and put that into a set. And so that's nicer. You can see it's somewhat simpler and maybe a little easier to understand. But there's a problem, which is that values on a contains on a values collection is often linear, because in a maps are geared for finding keys quickly. But if you want to say, does this map contain a value, most maps have no choice except to search every single entry. And so that's linear. That's just a shorter way of looping through every value. So the problem is, even though that code is nicer, it's still n squared. And actually, so just, sometimes people say, oh, nobody cares about algorithms. With the number of elements this guy had, it would take over 1 second to perform this operation. And so with the solution I'm going to show you, it actually dropped it down to less than 10 milliseconds. So if you have 15,000 elements, you do have to make sure that you're avoiding quadratic algorithms. Okay, so what are we going to do about this? Well, the problem is if value does a linear search, if contains over the values collection does a linear search, why don't we pull those values into a hash set, and then contains is constant time operation. And so that should reduce the strength of this algorithm down from quadratic to linear. So that will look nice. So what does that look like? Okay, so instead of doing contains over the values view collection, we'll create a temporary hash set and then call contains on that hash set. And that does work. That is much nicer. That reduces this to linear time. It reduces the whole thing to linear time. But I think we can still do better because this is a fairly complicated stream operation here. And I don't know if we need to do a stream for this. I'm a big fan of streams. Maybe you've seen some of my streams talks before. But there are times when you don't need them, and there are other ways to do it. And so I'll show you how that is. Okay, so one bit of insight is if you remember the original problem statement, it says, something, 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 values that occur in both maps. Well, that's a set intersection operation. And in fact, collections have operations that do set intersection for you. Now it's not obvious, but the method that performs set intersection is called RetainAll. And so it modifies its argument, it modifies the receiver. So if you look at this, if you start off with collection A and you say RetainAll B, it says, okay, so if there's some overlap there, it removes the parts of A that are not in B and retains the parts of A that are also in B. And oh, what do you know? That's set intersection. And so you can see that right there. So let's think about using RetainAll in this. And the other thing is, remember, we have these view collections and you can perform side effects on them, including removal of elements. And if the values view if the collection you're operating on is a view of a map, then it will have side effects on that map as well. So we're going to do this bulk RetainAll operation on the values view of one of the collections. And so since that has side effects, we might want to make a copy first, but that's another linear time step. And then finally, since the problem statement wanted only the keys, well, we know how to do that. We can just get the key set view. So that's what this code looks like here. So the first line is making this copy of the values into a hash set. So that's the same as before. But then the second line is we just make a copy of map B. And then, so the third line is really where it happens. We take the values collection and retain all of the elements that are also in the A values collection. Now what's interesting is the way this works is RetainAll calls contains repeatedly on its argument. And that's why it's important that contains be fast on its argument. And we've done that. We've taken care of that already because it's a hash set. So once we've done that, map B copy contains the entries that we're interested in. And finally, we want the keys that we're interested in, so we say, hey, just give me the key set from that. And that's our answer. So again, I like streams, but you don't need streams here. Just use a few collections bulk operations. All right. So quick summary, part one. Know and use the view collections. I think the map collections are not very well known. The map view collections are not very well known, and there's some interesting things you can do with them. And also, they're particularly powerful combined with bulk operations. They're the existing ones like remove all and retain all and contains all and things like that that have been in collections from the very beginning. But there are also some other ones like remove if, which I demonstrated earlier, which takes a predicate, and that's a nice bulk operation that you can parameterize with Lambda as well. And sometimes that's all you need. All right, let's move on to part two. All right, so sorted collections. So there's a whole family of types and implementations. There's sorted set, sorted map, navigable set, and navigable map, which have basically subtypes of the respective sorted parents. They just have more APIs. I'm actually not going to go through all of those APIs. I think there's some reference works, which I'll mention at the end, which cover those adequately. The implementations of these interfaces in the JDK are tree set, tree map, and in the concurrent area, there's concurrent skip list, set, and map. And through the rest of the presentation, I'm going to be talking about sorted set. But really, this applies to not only sorted set, but also sorted map, the keys of sorted map, navigable set, the keys of navigable map, right? So just for shorthand, I'll say sorted set. But the interesting thing about sorted set is that if you're going to sort things, you need to provide, what ordering are they in? And the ordering is provided by a comparator that, in the general case, the programmer must supply. There's also some stuff with having, you can have a comparable object that has a compare to method, and so that's referred to as the natural order of some objects. Those can also be used, but the same issues apply between comparable objects and supplying a comparator. And so, for the most part, all the same issues apply. So I'm just going to focus on comparators for the remainder of this talk, and the same issues apply with comparable objects. Now, and then the property that very, very few people understand about comparators is that they might or might not be consistent with equals, and I will cover what that means. Okay, so, but first, a brief introduction about sorted sets. All right, so if you look at hash set and set.of and those sets, the iteration order for those sets is undefined. And so if you say set of A, BB, CCC, and so forth, and print it out, gets printed out in iteration order, and it's an apparently random order. It is, okay, and then same with a hash set. So if you load a few strings into a hash set, you will iterate them in another apparently random order. And what that ordering is based on is a much longer discussion. Kind of doesn't matter. The point is that you cannot rely on any particular iteration order out of a hash set or one of the sets returned by set.of. Now, sorted set, the iteration order is defined, and it is defined using the comparator or the comparison method. And so, and that's why these are useful, because it's like, gee, I want a set, but I want things to be in a particular order. So I'm going to specify a comparator to impose that order. All right, so a comparator is a interface. It has it has a bunch of other methods, but the main method is a method called compare. It takes 2 arguments of type t and returns an int. And that int shows the relative ordering between A and B. So if that int is less than 0, it means that A is less than B. If the return value is 0, it means that A is equal to B, asterisk. And if the return value is greater than 0, it means that A is greater than B. Now, sometimes you'll see people checking for comparison with -1 and 1. Those are common return values, but the comparator need not return -1 or 1. So you always have to check for less than 0 or greater than 0. There are a bunch of rules you need to follow, which I've given in other conference talks, but I'm just going to list them here. Basically, it's intuition. If you have an ordering, then it has to be consistent with itself. It needs to be transitive, reflexive. It has to be a total ordering, which means that given any 2 values, there has to be a result. And in fact, most orderings are this way. So if you consider a bunch of strings, if you consider them in alphabetical order, case sensitive, that's a total ordering, because given any 2 strings, one is going to be less than the other, or one is going to be greater than the other, or they're going to be equal. And okay, I think everybody understands that. So I'm not going to spend any more time on these rules. Instead, what I'm going to do is talk about comparators in action. Okay, so I'm going to declare a variable here, which is a comparative string, and this is a case-sensitive order, so I'm calling it CSO. And that's going to be a method reference, which is the string compare_to method. Okay, so now CSO, so it's a Lambda expression, blah, 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 but the main thing is that it's a comparator. So, so it has a compare method. So I can say CSO.compare A and Z. All right, so the return value is less than 0, so that means A is less than Z. Okay, very good. Now compare Z and A. The return value is greater than 0, so Z is greater than A. And if I give it 2 equal strings, the return value is 0. Hey, pretty simple. All right, now let's use this in a sorted collection. Okay, so I've predefined a list of strings. I think it's a list, yeah. It has a bunch of strings in it. Let's create a tree set, which is an instance of sorted set. And as an argument, we give it a comparator. So I'm going to give it the case-sensitive order comparator. So there's nothing in it, so what I need to do is add all of the strings in that strings list. Okay, so remember, strings is in this non-sorted order, but if we print out the tree, they're in sorted order because we said let's impose a case-sensitive order on this tree set. Okay, so that's pretty good. Now the nice thing is, as you change things, the tree set keeps things in sorted order. So I'm going to add something. So if I eyeball this, we know alphabetical order. So CZ is going to fall between CCC and DDDD. And indeed it does. And let's add something else here. And so where does that go? This is a case-sensitive order. And so in ASCII or Unicode, capital letters come before all the lowercase letters. So the capitalized T comes first. Okay, that's nice. So this is just like a sorted list, right? Well, no. So let's create a list and play around with it for a while. All right, so I created a list, and let's add a duplicate element to it. So you can see there that I have a bunch of strings, and there's 2 instances of the string BB. And so let's sort this by our case-sensitive ordered comparator. So if we print out the list, they're duplicates, which are equal to each other, so they end up next to each other. So let's see. All right, so let's reuse this. Okay, so I cleared the tree, so it's empty. And so now I'll say tree.addAll of that list. All right, so list has that. What happened to the duplicates in the tree? It's a set. So duplicates are not permitted in a set, so duplicates are compressed out. So sometimes, a sorted set is very powerful, but it's different from a list, right? Lists allow duplicates and sets do not. So it's a little easier than you might think to fall into this trap. I mean, I'm telling you this right now, so it's obvious, right? But when you're in the middle of programming, there are a bunch of issues where people are surprised. It's like, what happened to this? It's like, oh, that's a duplicate because this is a set. Okay, so that's why things are missing. That happens more often than you might think. Okay, so now there's another thing going on here, which is that this issue of set membership. So if you read the specs carefully, it says set contains no 2 elements A and B where A dot equals B is true. Okay, that makes sense. So that's the definition of, how do you know something is a duplicate? Well, according to hash set, it's a duplicate if A dot equals B is true. A sorted set is different. And actually, this is kind of a problem. There's some inconsistencies in the specification here. But a sorted set says, such as a tree set, it says contains no 2 elements A and B where compare A comma B equals 0. That's different from calling equals, right? So they're different methods. Equals is a different method from a comparator's compare method. So first observation is that the compare method imposes an order on the sorted set, but it also determines membership. And so whereas we had a list, if we sorted that list in order, the duplicates ended up next to each other. In the set, it says, oh, those are duplicates. We don't have duplicates in the set, and so those are left out. So The comparator imposes order and determines membership. Okay, so remember, earlier I said, oh, if the comparator returns 0, it means A is equal to B, asterisk. Well, no, I have to start hand-waving here a little bit. This is where we're starting to get into the weeds here, because the comparison method is not necessarily the same as equals. And so when the comparator returns 0, it means that A is equivalent in some sense in the context of this ordering, which is imposed by the comparator. We're not talking about the object.equals method anymore. Object.equals is actually not used in treeset, and this is news to people, and it's news because it's actually not described very well at all in the specification. One thing that is interesting is that if you have a tree set and you supply a comparator, this notion of equivalence, the comparator returning 0, is provided by the comparator, which is different from the objects themselves, right? Objects, all objects in Java have an equals method. And so if you define an equals method for two objects, then those objects know that they are equal to each other. But the comparator comes from somewhere else. And so the comparator might consider two of these objects to be equivalent, and that might be different from whether those objects consider themselves to be equal. All right, so there's this terrible wording in the specification here. So this is all quoting from the specification. But there are these weird things that appear in the specification here where it says, so if you establish a difference between equals and the comparator returning 0 does not necessarily have to always occur when equals is true. And so how do you describe that? Well, that means that this comparator is not consistent with equals. So what happens if you do that? It says, if the ordering imposed by C on S is inconsistent, the sorted set or map will behave strangely. Well, thank you very much. Right? Okay, so now if you look at the sorted set I mean, there's just more of this stuff. And set is defined in terms of equals. Sorted set is defined in terms of the compare method. So that two elements that are deemed equal by this method are, from the standpoint of the sorted set, equal. The behavior of a sorted set is well defined even if its ordering is inconsistent with equals. It just fails to obey the general contract of the set interface. Okay, so I have to say that this is a remarkably obtuse piece of the specification. Now, I know what it means, but it's one of those things where you can't read the specification and understand what that actually means. You have to understand what's going on in the whole rest of the collections and then say, oh, that's what that means. But it is absolutely not explained well, and this is a source of a bunch of confusion and, in fact, a bunch of Stack Overflow questions. So let me try to explain what this does by way of a demo. All right, so remember, we had the case-sensitive order comparator. All right, so CS.compare, that returns 0. So according to this comparator, those two strings, lowercase a, are equivalent. Does a.equals a? Of course it does. Now, I'm not going to demonstrate for this, but for the space of all strings, I believe it is true that the case-sensitive order comparator will return 0 for any two strings that are equal to each other, and it will return non-zero for any two strings where equals returns false. So, and I think that's pretty intuitive. Now let's, okay, so let's, but if you think about that, what's a comparator that's inconsistent with equals? That sort of doesn't make sense because, it's all sort of abstract. What does it mean to be, we can sort of touch on the idea of what it means to be inconsistent with equals, but, how can those exist? So I'm going to show you one. In fact, there's some built into the JDK that have been there forever that nobody knows about. So I'm going to create a new comparator called case-insensitive order. And there is a comparator built into the string class called case-insensitive order, CIO, case-insensitive order. So if I do CIO.compare of lowercase a to lowercase a, that's 0, of course. Now, if I do a case-insensitive comparison of lowercase a and uppercase a, well, we said compare case-insensitive. So it says those two strings are equivalent. So it returns 0. That makes sense. Does lowercase a equal capital A? Of course not. So this is a comparator that is inconsistent with equals, right? So you have one right there, right? So sometimes you hear people say, oh, well, you mustn't have comparators that are inconsistent with equal. If you have one of those, that's a bug. Well, no, I'm sorry. There's one right in the JDK. People use it all the time because doing a case-insensitive sort is very useful, but in fact, it is inconsistent with equals, as you can see on the screen. Okay, so what happens if you use this with a sorted set? Remember this strange behavior. All right, so let's create a tree set that uses case-insensitive order as its comparison. So let's add a few strings to this. All right, so I added capital M, lowercase a, and z. And so that got sorted. Now, remember, capital letters, if you're case sensitive, capital letters come first, but if you're case insensitive, M comes between A and Z. So that's why capital M got sorted in the middle. All right, that makes sense. Now look at this. So let's see what contains does. Okay, the tree set contains capital M's. Well, does that make sense? Well, I asked for a case-insensitive comparison, and so if you're looking for something regardless of case, and you ask for lowercase m's, it says, yep, I got that. All right, so let's create a hash set and copy the elements into it. Yeah, okay, so you can see that has that, so the hash set contains capital M, but it doesn't contain lowercase m's because hash set is using equals, and lowercase m's does not equal uppercase m's. All right, so are these sets equal to each other, though? Okay, how do you know if two sets are equals? They're equal if they contain the same number of elements, and if every element of the argument set is also contained in the receiver. So that's true. And that's true as well. Now let's change one of the maps here. Let's remove the lowercase ones and add remove the uppercase m's and add the lowercase m's. All right, so are these sets equal now? Okay, so you can see that the hash set contains lowercase m's, but the tree set contains uppercase m's. And so if we ask the hash set whether it equals the tree set, of course it's different because, hey, they have different strings in them. Somebody's chuckling. They know what's going on. Oh, how did that happen? Let's work through the algorithm. Tree.equals hash. Okay, they have the same number of elements. We step through the elements of the hash set. Lowercase a. Is that in the tree set? Yes. Z, lowercase z, is that in the tree set? Yes. Lowercase m, is that in the tree set? Case insensitive comparison, yes. Well, because uppercase and lowercase m's are equivalent in the case insensitive order, yes. Contains returns true, and the tree set considers itself equal to the hash set, but the hash set does not consider itself equal to the tree set. And so this is an example of some of the strange behavior you can get. So I'm running out of time here, but I'll try to give you a, so I have a quick, simple example here of if you have a list of employees, and basically they just have names and salaries. So that's a list, so let's sort that. All right, so employee is a real simple POJO. It has getters on it. And so what I'm doing is I created a, all right. Yes, thank you. Okay, so let's sort this list of employees by salary order. Sorry. All right, so now, where's my for each? Okay, so it comes out, they come out in salary order. So let's load these into a tree set ordered by salary order. So what's going to happen? So that's the list of employees, but I copied them all into a tree set, and Pat is missing. The reason is we sorted them by salary order, but remember, the comparator also determines membership. And so Pat and Terry happen to have the same salary, and so Pat is going to be really mad when they don't get their paycheck at the end of the month. All right, so you have to be very careful about using comparators that are inconsistent with equals. That's the second demo. Basically, don't mix tree sets and hash sets because you get these weird asymmetries in behavior, okay? And finally, here's, if you want to find out more about collections, Morris Naftalan has a book about generics and collections. I will be at the Groundbreaker Hub tomorrow at 1:30 if you have any questions. I'll be doing open mic there, so please come by. Thank you.